Hello everybody, this is Dr. Hussein. We are in module 3 for power electronics, which have the title inverter and AC controller, and this is week number 8, where we are going to start discussing the DC to AC converter, which is simply defined as the inverter. Now in this week we are going to discuss the single phase inverter with its harmonics and different techniques used to control them. After that, in the next week, hopefully we'll start with the three-phase inverter. Now, the idea of single phase inverter, let me start from switch mode DC to AC inverter. Have a look. Now you remember, usually what we have AC input, okay, which is either 50 or 60 Hz single phase or three phase, and our loads mainly is AC motor. So if we talk about air conditioning, if we talk about any machine in the industry, we are talking about AC motor. Now, how we can make our circuit to control the output going to the motor? Very simple. We use diode rectifier to convert into DC. So here we go DC. Definitely we need capacitor to smooth the voltage, and then here we will have inverter. As you can see here, I make just a switch to make it open. If we have 2 switches, 4 switches, 6 switches, and so on. So now this DC will convert to AC again. You say, okay, what is the point? It was AC, you converted to DC and then back from DC to AC. Yes, correct, because this AC it's not controlled. It's giving me 230 volt frequency, 60 Hz as example, or 50 Hz. But here at this point, no, I control the frequency, I control the voltage, magnitude, and so on. Now, this circuit can be improved to contain switch mode on either side, on the AC side here and the AC side here. It means rather than I use diode switching circuit, rectifier circuit, I use thyristor. What is the benefit from this circuit? This circuit will work in dual direction. It means energy can come from here to here, so we have inversion mode. This is rectifier and this is inverter. And if we have energy to return to the supply, as example in AC braking, electrical braking, sorry, we have energy going back from the load to the source. Now it can, because here we have control switches. Now this one will act as a rectifier, okay, and this one will be the inverter one. Now this circuit we could connect between the AC and DC parts a capacitor, so we call it voltage source inverter, as you can see here, VSI, voltage source, or we can connect inductance link between them, DC link between them, which is called now current source inverter. I mean, there is not much difference between them, okay, however they have different applications, but most of the circuits are voltage source inverter. If we would like to classify them, we will say first one is the pulse width modulation inverter. In this inverter, the input voltage is constant, DC, let me say. Okay, we can control by pulse width modulation the magnitude and the frequency of the output. The second one is square wave inverter. Here the DC voltage is uncontrolled, okay, is constant, but we control it to control the magnitude. We need to control it, increase it or decrease it to control the magnitude. Now single phase inverter with voltage cancellation, let's make sure that this is only for single phase inverter, not for three phase. But we use the principle of voltage cancellation, as I will explain in this session, okay, that we can control the magnitude and the frequency by cancellation. Now here we have DC, okay, and we are going to come up with AC. So VDID coming from rectifier circuit as example, and here we have our inverter plus its filter to come up with, as you can see here, instantaneous, because it's small letter, instantaneous current and voltage. How it look like? It look like this way. And definitely we have here the current and voltage are phase shifted between them, phase shift, okay, and the operation of this circuit is in 4 quadrant. In quadrant 1, where it works as inverter, okay, both current and voltage are positive. In quadrant 2, where rectifier, the voltage will be negative. Okay, here the voltage will be negative. In quadrant 3, the both voltage and current are negative. In quadrant 4, we can see that the current will be negative, as you can see here in quadrant 4. Now let's start with one bridge, one leg inverter, leg A, as you can see. In leg A, we have switch TA positive, which means that switch A of leg A, but connected to the positive side, and TA negative connected to the negative side. And definitely we add here anti-parallel diodes as a freewheeling diode, as we explained before. And this VD, let's assume we have two identical capacitors, which theoretically, hypothetically speaking, okay, so the voltage VD will be split here into half here and half here. Now let's see the voltage between the point A and the point 0 here. If we put load here, how the load will see the output voltage coming on. Have a look. Before I start discussing that, let me start with some terminology, because we are going to use them. The first simple to define here is FS, which is the carrier frequency, the switching frequency, okay, because we have carrier and we have control signal to find the output. And F1 is the modulated frequency. It means the frequency I want my output to have. As example, 50 Hz, then F1 should be 50. 60 Hz, 60. And also, let me define, based on Fs and F1, the frequency modulation MF to be the switching frequency over F1. Okay, carrier frequency over modulating frequency. Now, usually carrier frequency is high, talking about kilohertz, and here is in hertz, so we expect MF to be high. Also, let me define MA, the amplitude modulation, to be the comparison between V control and V triangle. Just a minute, it reminds me with the same discussion for triggering thyristor and rectifier circuits, and for controlling by pulse width modulation DC-DC converter. We discussed them before. Yes, it's almost the same. Now here we can see that when V control, I will show you on the graph next slide, greater than V triangle, TA will be positive, and the voltage here between A and O will be VD over 2. But when it is negative, less than, so TA negative will work, it will be negative voltage, the same voltage but negative. So just a minute, it looks like the output will be positive, negative, positive. Oh, this is what we talk about AC. This is the definition of AC. Okay, this is my one leg switch. Now this here, I can show you the comparison between V control. V control, the sinusoidal waveform here. It is similar to the waveform I want on my output. Okay, and V triangle, this is V control, and V triangle is this triangle, okay, in this way. Okay, so we compare them. Now let me start with assuming that VA less than 1, because we are going to see later when it is greater than 1. What the meaning of VA less than 1? Just a minute. VA is V control over V triangle, and as you can see here, the peak of the V control here is always lower than V triangle, so always MA lower than 1. This is the situation of what we call it linear mode. Okay. Now when we compare, as example, V control greater than V triangle here, there is pulse, okay, and otherwise is pulse going to the negative. Okay, so this comparison will give me this waveform, as you can see here. See here, this waveform. Now have a look at this part and this negative part. It looks like something close to sinusoidal. Okay, here are smalls and here are large. Now with filter we can make it sinusoidal. Now if I come to the harmonic spectrum, I will find that I have the fundamental, or let me say, frequency modulation with its signed band. Okay, much harmonics here. This need to be considered. Look, we want to convert from DC to AC, but we want it to become pure clean signal. Otherwise, if my waveform is not clean with many harmonics, it gets heat to the load, heating the load, and it disturbing the load, and the load will not will not work effectively. Now, what about the peak magnitude of the fundamental frequency component? How we can deal with it, and how it affects my output? My output in the previous one, the linear modulation, when MA lower than 1, is equal to VD over 2, as I explained. Have a look. The output voltage is V control over V triangle, because through this we control, by VD over 2, as we mentioned. But V control is a sinusoidal waveform. So if I take this part and substitute it here, I got V control maximum over V triangle maximum sine VD over 2. And this part is MA, as you can see here. So it seems to be the fundamental voltage is MA times, forget about sine is giving the trigonometry property, but VD over 2, as explained. You see here, MA times VD over 2. The harmonics in the inverter appears, as I mentioned, sidebind harmonic center around the switch modulation, and it can be written in this way: F harmonics equal to J MF plus minus K by F1. This is the formula used for inverter, and harmonics will be MF plus minus K, as we will explain in the table. Next slides. Now you can see here, this is the control. I try to expand it, okay, V control, and this is the triangle, as you can see here. Okay, let's zoom this one to see what happened. Have a look. This is the control signal, and this is the triangle. Now from here, as example, from this point to this point, V control greater than V triangle, so we have pulse. But from this point to this point, V triangle greater than V control, so we have negative pulse. This is how it look like, how it works. Minus 2. At MF, I need to multiply by this point 818. If it is MF plus minus 2, I need to multiply by 0.22. As you can see here, I multiplied 0.22 for 41 and 37, and 39, I multiplied by 0.818, as I explained. This is the voltage for each harmonics, and we can go further. Here, as example, I'm 2 MF plus minus 2. It will give 77, 79. And for the frequency here, for each one of them, as example, this is 37 times the fundamental, 47. This is 39 by the fundamental. This is 41 by the, and so on. That means the frequency at each, for each voltage. Now for overmodulation, when MA greater than greater than 1, okay, it's not anymore linear. It's become overmodulation. And overmodulation, as we can see here, the sideband harmonics reduce, but we can see we have a rich spectrum. As you can see here, we have the first, third, fifth, seventh, and so on. Now this graph, okay, show me the linear modulation and overmodulation. For linear modulation, when we have MA lower than 1, you can see the curve is linear. This is the ratio of the voltage from the table. And when it becomes greater than 1 here, you see here, I moved greater than 1, we have overmodulation. We have curve. Until we reach pi over 4. I will show you why pi over 4 later. We will reach here what we call it square wave. After that, square wave. A few points is worth to be highlighted here related to MF, frequency modulation. When MF is small, what do you mean by small? I mean lower than 21. Greater than 21 mean large. First of all, synchronous pulse width modulation is a must. What does this mean? It means that, have a look, this is the square wave. Now my control signal supposed to be start together and let me say here and finish together. If it finish here, as example,